Welcome everyone to the last webinar of the year. So today we have Dr. Kanish Chayaki, who will present a machine learning model in autonomous driving from theory to practice. And in the meantime, I would like to advertise the next webinar in next year, January, which will be computational intelligence for disaster planning and mitigation on 26th of January. So if you are interested, you can register to that webinar. So now, today, please welcome Dr. Kanish Chayaki for the talk. So, Dr. Kanish.
Yeah, thank you. Thank you, Dr. Sansani. Thank you. Okay, hi everyone. So, can you guys see my screen?
Okay. Yes.
Can you see? Okay, cool. Yeah. So yeah, hi everyone. Yeah, my name is Kanishka, and I'll be talking about the machine learning models and in autonomous driving, and how do we actually achieve them from our theories to a practical point of view. So the webinar will be divided into 5 different parts. So before that, let me just go through just a brief introduction to who am I. So yeah, I work at Active Advanced Research Center in Aurora Hills, California, and I have a PhD degree in electrical engineering in machine learning from UT Arlington. I worked before on machine learning right from my undergrad, so I've been doing this when it wasn't that cool. And right now, I work on primarily on radar machine learning, doing all sorts of different things in there, from doing radar super resolution to classifying moving objects to doing early debris detections for stationary objects. So, and then I develop good amount of intellectual property around radar machine learning. So that's primarily about me. Now, this one I had to put in because of my company lawyers. All the figures and presentation in this presentation is taken from the Google research, and everything is available in public domain. So I'll only be discussing things that are there available publicly. Okay, yeah, so what's the workflow of this webinar? So first I'll introduce, just motivate the problem of why do we actually need autonomous driving? And then I'll go through what kind of sensor and the hardware stack that we use. And then coming to the software, I'll give an overview of the machine learning and how do we use it. And then get into details of it and what specific models do we use. And I'll just take one example. And I'll close this webinar with a case study of how do we do a drive scene understanding in an urban area. So let's get started. So yeah, let's see. Why do we need autonomous driving? So human beings are terrible drivers. The data suggests that. And a majority of the accidents that happen are because of the human element, that they are not paying attention, they're sleeping, or, you know, they're just not doing things right. So our roads will become much safer if we do an autonomous driving. We'll save a lot of gas money because it's going to be more efficient and more optimized when cars are driving by themselves. There will be less traffic congestion because cars will be driving in an optimal distance with each other on the road. And I can vouch for this being in LA. Yeah, human drive is really, really bad. There will be less amount of carbon emissions, so the environmental gains are there. And then we can free up parking lots for many other users. And then the last one is the model subscription-based service. So that makes more of a business sense in the sense that think of it like Netflix or on any of the subscription-based streaming services. The idea is that in future, we're not going to own the car, we'll just subscribe to the car. And once we summon a car or we ask for the car just comes by itself, use it, and then it goes by itself. So we don't really own a car. And we are already in the transition mode right now with Uber, Lyft, and all these Didi, all these sort of car services that we have. So that's more of a transition model that these guys have. Okay. So what are the typical driving tasks that we have in a regular scenario? We have a lateral control. We have something which we steer. We do a lane change. Then we have a longitudinal control where we either accelerate or we brake, and then we do a cruise control. And then we also have to protect ourselves from the objects that are coming in front of us or next to us, like stationary objects, moving objects, or near moving objects like pedestrian. And then we also do a planning when we drive. We say, hey, I'm going to go from point A to point B. What's the route I should be taking? Sometimes it's you want to take a longer route with no traffic versus smaller route with a lot of traffic. So you do a lot of planning. So these are the main sort of tasks that a driver undertakes when he drives a car. Now, where are we right now, and where are we going to going ahead with this? Level 0 is something that we have right now, a typical human driver driving and taking care of all these tasks that I mentioned. Level 1 and 2 is something which already are there in the cars. You can see all sorts of like major OEMs, they have them. Level 3, 4 is where we are doing the research and development right now, where we are trying to go. So level 4, the closest we can see is probably Waymo, and which are very, very close to level 4. Level 5, I mean, it's far ahead. It's going to take some time for that, and there are a lot of challenges for that. So that's there. Okay. Now, the main problem, as you can think of, the lateral and the longitudinal control is not the problem. The problem is when you see objects in front of you, and how do you respond to that? So what we have is an detection, recognition, and classification of stationary objects, moving objects, and near moving objects on the road. And this is a task. And based on what you see, you have to have an appropriate response for that. So you see all sorts of things on the road. I just put up some examples here. Some accident happened on the road, so you see a lot of things from there. There is a landslide. There are objects on the road. I mean, some countries have that, like some animals are on the road, and you have to sort of sense them. You don't want to run through them. And then also you have to see these speed signs and all these stop signs and all the signs that are put together by the DMV. And you have to drive accordingly. So these are all the things that you typically see on a road, and you have to have a response for that. So how do you do that? So I'm going to go through that in detail. Okay. So yeah, what's the sensor that we use? All sorts of sensors, and what kind of hardware do we use? So I'm going to talk about this right now. Okay, let's see. What are the sensors that we have in autonomous driving? So typically, camera is the most common, the most cheap sensor that we have. Here, what I'm showing is camera, LiDAR, and a radar. These are the 3 most common sensors used. And each of them have their own advantages. But then ideally, what one would like is sort of have a fusion of all these. But then again, there are some business constraints in a car that I'm going to talk about, that why we cannot use certain sensors as such. Nothing to do with technically wrong, but it doesn't make aesthetic sense sometimes. For example, LiDAR. Nobody wants a LiDAR on top of their car, like a siren, like a police siren. I know I mean, imagine a Ferrari or these Porsche or any of these luxury cars. You don't want a LiDAR on top of the car, so the customer is not going to buy. So all these things are also motivated by what the customer demands. So LiDAR has a big issue with that, although LiDAR is very good in terms of creating a 3D point cloud. So in terms of object detections, the LiDAR is good. I mean, you can see it here. The camera and radar are kind of okay. If you fuse them all together, they work perfectly. And then fusion by itself is a good research problem of how do you do all sorts of fusion with different sensors, and how do you take sort of a voting if two sensors are agreeing and one is disagreeing. That's easy, but if what if the one that is disagreeing is a minority, but actually it's the right answer? So it's a good research problem to solve. And then again, what else do we have in an autonomous car? We have a GPS, which kind of tells us where we are in the world. The IMU, which sort of measures the vehicle movement and location by tracking the speed and acceleration. And then also we have a wheel odometer, which kind of calculates the orientation of the car, where is it going, and then the overall speed. We also use the wheel odometer for calculating the positional drift and what's the speed accuracy. Why do we need speed accuracy and drift? Well, we need them because to have these advanced safety detection algorithms or stationary object algorithms, we need to have very accurate measurements of speed of the car. So here I'm just showing one of the examples of what's a typical sensor setup. And again, by no means it's exhaustive. By no means it's the only way we do it. There are many ways of putting the sensors. Depends on different car manufacturers, different OEMs, and different places, different situations. So we have the front-looking radar here, which is mostly the far-range radar. The radar on the right and the left are mostly medium-looking radars, which are mostly used for something coming in your lane or mostly for parking. And of course, there are other sensors that are used for parking also, but I'm showing an example of radar. The camera in the front is mostly used for street light detection, whether it's a green or a yellow light and a red light and all. And is there any other object coming in front of us? The LiDAR, again, as I said, it's on top. There is a camera on the sides, which is mostly that you see it right in the middle, the left and right camera in the middle, which you see. Those cameras are mostly for things that are going on the side of your car. That's one. And then the radar on the back kind of helps you to take a reverse gear if you're trying to sort of get your car out of a parking lot, for example. So that's where it's being used. This is more of a detailed setup of how does the car looks like, and I'm just putting one example. This is you can Google it up and kind of see the details of this this setup. What we have here, and as I was saying before, there is the image previously shown is not the exhaustive setup. This is another setup that we have. Here we have all the computers, all the equipments for the computation is all the way in the car on the backside. In the front, we have these long-range LiDARs, and the ESRs are basically the electronic sensor radars. These are the long-range radars. And then you have the short-range LiDARs on the sides. And then, of course, you have the trifocal camera, which is in the front to detect the traffic lights and all. So this specific setup we are currently using in the Lyft taxi service in Las Vegas. So yeah, if you call up a taxi from Lyft in Vegas, there's a good chance the active car actually comes in, and it's I would encourage, like it's pretty cool to sit in it, and it's looks surreal, but it kind of scares you out sometimes when you see the steering wheel kind of doing its own job by itself, and the driver is not doing pretty much anything. So it's kind of cool. Okay, so let's see what kind of hardware do we use. So the hardware that here I'm describing is not just in the car, it's also for what we use for developing the machine learning algorithms offline. So, and whatever the machine learning model goes in, that goes onto a chip or an embedded controller that goes into the car. So just to give you an idea, a common question that always been asked to us is, well, why don't you just put a GPU in the car and it's gonna, you can put all sorts of advanced algorithms. Well, you have to think of it this way, that every car has the profit that the car manufacturers make is by volume. So even a 1 cent increase in the car manufacturing, it kind of costs a lot. So it's very hard to convince any OEM to, put $1,000 or a $500 GPU in the car. So it's really hard. Like cost is a big factor that goes in. So most of the time, what OEMs want is their own custom hardwares. Although there are some open source hardware existing, but mostly we design our own hardwares, and there is a separate hardware team for that. And then what the hardware does in the car is just take data from all the sensors, the GPU, the IMU, the LiDAR, radar, or whatever sensors they have, and then make a common decision based on the algorithm that's there. For offline hardware, the way the workflow works is you have a proof of concept on a simple laptop or a regular laptop with a very weak GPU. You see the concept is working, and I'm talking here very specific about how do you do the R&D on that. So you have an idea, you have the research problem there, you kind of solve it on the laptop, show it on a small data. It goes on a workstation. You can take any of the high-end workstations. I mean, here I'm showing the NVIDIA, but you can have the Lambda workstations, which are pretty good. And you kind of run it on multiple GPUs now. So running it on multiple GPUs, any of your machine learning algorithm, it kind of helps you out to sort of make sure that, yes, this is going to run on multiple GPUs on the cloud. And then later on, you deploy it on the cloud, where it runs on sort of thousands of machines, and you get a trained model. So most of the time, the machine learning algorithms that I use most of the time are supervised learning. So there's a lot of effort on labeling. So there are a lot of internal tools that companies use for labeling the data that we have. And then as far as, and another common question that's asked is, how is the timing being set when you have all these sensors in the car? Well, mostly the GPS is used for timing different sensors and modules, and it kind of provides a common clock to all the sensors, because frames are, to give an example, radar runs a little faster in terms of sampling compared to, let's say, a camera. So you have to time both of them, and if I go into more details of it, timing all the sensors on a common clock is a very crucial part, actually. All your sort of outcomes of the machine learning algorithm are going to go way off. If your number of frames, the frame at which you are in a camera, you should be exactly at the same frame in a radar, and the same frame in LiDAR. So all, and you, of course, the timestamp has to be the same for all. So yeah, I can go on this, but this is one problem that we usually deal with pretty much like every day. Okay, so yeah, that ends that part. Now I'd like to go into just an overview of how do we use machine learning in autonomous driving. So how do we start? So to start with any machine learning problem, we need data. The way we divide the data is in highway settings and in urban settings. Now, why do we do that? Well, because the highway setting, it's an easy classification for the data, and to again, thinking of it from a dynamic programming point of view, you want to solve a bigger problem, you got to break it down to smaller ones. So the smaller way of doing it is first solve the highway problem, having autonomous driving in highway, which is fairly easy to do compared to an urban setting. So you would see that there is most of the manufacturers or other OEMs, they have pretty much autonomous on the highway settings because it's relatively easy. Now, why is it easy? Even though the traffic volume is high, and the speed is high, the number of lanes are much higher in a highway setting, and then the intersection and the turns where most of the corner cases comes in, they are very, very few on a highway. And I'm talking about any highway in any major country that you see. Now, an urban setting is a relatively difficult task to do, because not just the traffic speed is, even though it's a little bit medium compared to a highway, but the number of turns and intersections and are far more than highway. And then the objects, when I say objects, like it can be any pet, any pedestrian, any hawker, a lot of things comes on an urban setting. I mean, think of it like any major downtown of any city. You know, there are a lot of things there compared to a highway. So yeah, that's how we divide the data, and that's how the data collection is being done. So people collect data from these two different settings, from a crowded and then from a highway. So just to sort of show how difficult a simple task of lane changing is, and if I convert it into like how do you explain this into a machine learning model, I wanna analyze this highway maneuver problem. Now think of this this car here, this silver car, which is behind the truck. It's driving just behind the truck, maintaining a safe distance, and it needs to change the lane to the left. Now, it has to maintain the speed because there might be cars behind it. It has to do a lane change, and in case the truck in front of it stops, it has to do an emergency stop. So the driver has a sort of couple of tasks in hand while he's changing the lane. And when he's changing the lane to the left, there is a good chance the car, the blue car on this side, might also change the lane to the right. So they might clash. Yeah, there's a good chance for that. So the driver also has to make sure that the blue car does not change the lane when he's changing the lane. And he has to sort of speed up and come into the lane, the left lane, and then go ahead and then sort of go ahead of the truck. So you can kind of think of this as like, you can kind of break down into different steps and see that this is a tough problem to solve by itself. And that's the number of decisions you have to make when you're designing the machine learning model. So another question that normally comes, which is most like a common misconception, is that we don't use machine learning models which are off the shelf. We can actually. Many reasons for that. And first of all, the major reason is they're really, really big and they cannot be put onto, let's say, an embedded. So that's one. Unless we have like a really powerful hardware and all. So that's one thing. But then we have to do some custom settings, and mostly we have to develop our own algorithms, machine learning algorithms, and do the training on the specific data that we have. So transfer learning sometimes helps, but that's very limited to the camera data, but not to the radar or the lidar data. There's not that much of a publicly available lidar data except the Kitty data set that is there available. So how do we solve this, let's say, a highway maneuver problem in terms of a machine learning? So let's see that. So how does the pipeline looks like? So a typical ML pipeline is you have this huge amount of data collected, let's say highway, urban, any of them. It's being collected here. It's also collected while you're driving the car, and at the same time, once you've driven the car, and sometimes it's offline because there are multiple sensors and all, and then the real-time data collection may not be possible. So you just store it into a hard drive and put it into this data lake. Once you have it here in the car on a hard drives, you upload it on the cloud, and it stays in there like in a cold storage or in the hot storage, depending on what you want to do with it. Then the data is also taken by the labeling team because of the supervised machine learning problems. It's taken by the labeling team. They label the data by hand label it or semi-supervised based labeling. There are a lot of labeling tools that we use, and it's not just think of labeling. It's not just the camera labeling that we need to do. We also need to somehow map it to the lidar sensor or the radar sensor that we have. So again, I'm only focusing on 3 different sensors. So that's there. Then it goes on to training the best model that we have. And then you train and get the best model. You do a data simulation. The data simulation kind of helps you out what's gonna look like in real life. You fine-tune the hyperparameters of the model, and then you go again into the data simulation. You get the best model, you store it, and you deploy it onto the cars. So that's just a quick rundown of how do we actually do it. A typical, in terms of a software architecture that we have, is you have all these different sensors. You do a perception, you do a planning, and a controller. And then there is an environment mapping, which is mostly the maps that comes in. The maps kind of helps in understanding the perception problem. And based on that, we have an actuation, which is like, okay, what do you want to do with it? How do you want to respond to it? So this is just a typical software architecture. There are two schools of thoughts on how do we do machine learning for different autonomous driving tasks. So we don't really do just one task and just feed it all in and let that car drive by itself. No, we divide it into multiple tasks. So one way of actually looking at it is this, that you have a perception, you have a high-level path planning, you have some kind of a behavior arbitration, which is, if we call it low-level path planning, and then you have motion controllers. One way of doing it is you create physical models for each of these blocks, and we call it sequential perception planning action pattern, like it's block by block approach. The other school of thought is you just feed in the data and have the labels and let the neural net figure it out by itself, which is end-to-end learning. Again, each of them have their own advantage and disadvantage. I personally believe that the first one kind of makes more sense, because if any problem goes in any of these blocks or any of these tasks, you can actually isolate it and fix it. In an end-to-end learning, it's really hard to isolate the problem that you're facing. So that's there. So we're going to focus on the first one here. Okay, so ML in perception is where majority of the papers or research publications are there, perception. And by perception, what do I mean? I mean, all sorts of detections of traffic signs, of objects, classification. What do the object looks like? What are these things? You have to track, you have to see wherever the object is, you have to track it every frame. And then also you have to do some kind of a segmentation, which is very useful for urban maneuvering and urban autonomous driving. So it's the most important and the most complex task in an autonomous driving. So that makes sense because the majority of the paper comes in there. So I'll just show one example of how does the perception looks like. Let's say we have these sensors, we have the HD map, the high definition roadmap, we have the GPS. It all goes into different tasks that we have. So the HD map, it helps in doing the static object detection, the LiDARs and everything helps in the dynamic object detection. You put a bounding box, you do a tracking. After you track, you do a prediction of the motion prediction of the object, and then you have the dynamic objects being tracked, detected, and predicted, all of them together. So here I'm just showing in the software architecture just one specific block, which was the environment perception block. You can read more about this. I've given the reference for that. It's a pretty interesting course. So yeah. Again, if you see this LiDAR camera and radar, going into this object detection slide in more detail, what all detections do we do? Well, we do a lot of things in there. So we have the lane detection, the object detection, the 3D point cloud object detection, the traffic lights, all sorts of things. And here's just a simple workflow of how does it look like, what all things there are there in the car. How do we actually do a machine learning based perception onto that? So based on three different sensors that we have. As you can see, radar by itself has its own pipeline, which is the radar processing. And if anybody is into radars, they might know. I'm just not talking about the CDC level of the radar. I'm also talking about the low-level time series data that we have. So more on the spectrum level rather than the point cloud level. And then for the LiDARs, I'm just specifically talking about the point cloud LiDARs that are there. And these are just mostly, I would say, industry standards. The way we actually process these sensors, or at what point we sample the data and then we take them from the sensors. So that's there. So yeah, I'll dive deep into the machine learning for autonomous driving now, based on what I talked before. It's just a general learning framework. I think so what it means is basically what is learning and how do we use machine learning in there. So based on this learning framework, we have, of course, different neural net models that we do. So this is just a simple neural net model that I'm showing. One is a linear classifier, and believe me, this is very effective. In some of our cases that we see, you don't really need a fancy deep learning or all these, multi-headed neural nets and all. Sometimes the linear classifier or logistic regression works pretty okay. on simple tasks. So that's another thing. I mean, you don't just blindly put a deep learning model anywhere. You have to sort of see the problem and then figure it out. What do we really need for that problem? So yeah, that's one. And then here I'm just showing one multi-layer perceptron that's also being used. Again, it's more on the sides of the fully connected layer part, but sometimes depending on the problem, if we cleverly model it correctly, there are some cases where we've seen that a multi-layer perceptron kind of works. It's faster, it performs good, so that's there. Autoencoder structure is another one that we use mostly for resolving radar images or lidar images, or the camera, and it's also being used for different tasks inside. And then of course we have deep learning models that we use. So here I'm just showing an example of how do we stack different deep learning models and in an autoencoder, and to sort of make it into a stacked autoencoder model. Now, what are the problems with that we normally face in deploying all these ML models? So the first is that the hidden units and the output classifiers in a deep learner can be linear. So because the radar sensor and the camera sensor are there, most of the radar processing or the camera processing is linear. So you don't really need a highly complex nonlinear function to sort of solve a small task. I'll give an example. To do an object detection on a radar, a linear network is going to be pretty okay to do compared to a nonlinear network. Most of the features that are used in deep learning can be linear. Now that's another thing that we figured out, that as if you use just an off-the-shelf deep learning, let's say 5 or 6 layer deep network, you would realize that the more deeper you go in, depending on the problem that you're solving, if the problem is fairly linear or not highly nonlinear, you don't, by the time you reach, let's say, the 3rd or the 4th layer, the features become very linear. So you don't really need that many number of layers. That's what I'm trying to say. There is a lack of labeled data. We face a lot of problems on that. Hand labeling is expensive, and different sensors are, camera is still easy, but doing it on lidar and radar, it's hard. You need to train a person to sort of visualize or to sort of see what object does it looks like in a radar, because in radar it looks very different, or lidar looks relatively different than the camera. So, and there is a difficulty in sensor fusion. Like I said, you have to do some kind of a consensus building. And that's another good area of research, actually, where we do this consensus building of different sensors. And of course, there is a hardware-software gap. Even if you build a pretty good software, there are not that many hardware available in the market where we can deploy those algorithms and then put it into the car. So that's another problem. Now, this is one model that we kind of use. This is also from one of my previous research, which is a generalized linear classifier using a second-order Newton algorithm. But without getting into the details of it, the idea was pretty straightforward, that you can actually put a nonlinear activation on the outputs, and still, if you train it cleverly and correctly, it kind of outperforms a poorly trained multi-layer perceptron. So you don't really need a hidden unit as such. You can just do it with a nonlinear activation of the outputs. And I did a lot of things in there, sort of a lot of tricks on there. But then ultimately, it's so lightweight that it can actually be deployed onto an hardware. So that's where the good thing in this is. So that's there. Then we also have an adaptive multi-layer perceptron. Now, again, I'm focusing on smaller networks, and the reason for that is we need ultimately, no matter how good the algorithm you make, ultimately it has to go onto an hardware. And if it cannot fit onto an hardware, it's really hard to to sort of have any use of it in a machine in an autonomous driving case. So you really need smaller hardware, smaller softwares, or smaller neural nets. So this is another one that I developed, which is about having pruning the hidden units based on their usability. And I've given the references There is a public patent file on this, which is being used in a sorting machine right now. And then, yeah, the details are here. So I would encourage people to sort of see this and let me know if there are any questions and all. So this is just a commonly used machine learning models that we have. Of course, we have multilayer perceptrons. We even have generalized linear classifiers. Convolution networks by itself, not just for camera, and this is, I'm just showing an example here. Not just the camera, we also use it for LiDAR and the radars. And think of, there is a way of thinking about, let's say a radar, for example. I'll take a radar example. Instead of taking it as thinking of it like as a signal in a radar, just think of it like an image. And then you can do all sorts of image processing and vision-based ideas onto a radar sensor. The only difference being a camera is in a Cartesian system. Radar objects are mostly in the polar system. So it's a slightly different sort of coordinate system that we have. But convolutional nets are successfully used in not just the camera, but also for the other two sensors. So that's there. And again, because it's we have to track the object, so there is some kind of there is an inherent structure to the data, because one frame is connected to the other frame. Let's say on a highway, you kind of log the data and you have multiple frames. So it's very obvious to use some kind of memory-based network. So yeah, a recurrent net or LSTM and GRU, very common, and attention-based networks are also being actively used. Again, just to infuse some memory. One problem that we face with these memory networks is, again, not many hardware providers support memory networks on their hardware because it's really it's really sort of computationally intensive. So this is an example of, like, we made a good software based on memory network, but then it's hard to deploy it onto a hardware, a publicly available hardware. So most of the time we have our own custom hardware, but then there also we face problems, and also that can be another talk by itself. Okay, so yeah, what are the commonly used structures that we have? Apart from the residual learning, which we found very effective for training really deep networks, the unit-based structure, or the pyramid pooling structure that I'm showing here, H, is extremely useful. And then the channel attention, the channel attention is also useful for specific tasks. Again, each of these structures are good for certain tasks that are in hand. So as I said before, I'm not talking about the end-to-end learning. I'm just talking about block by block. So you just take each block, which is one task, and then you decide which of these structures are going to work for you. Just to give you an intuition behind these structures, if anybody's interested, the dense connections are something similar to the bypass weights in the multilayer perceptron that we used to have in 80s. There is a good amount of research on that, which basically what it does is that it takes out the linear part. So these connections that you see here, these sort of hopping connections that you see, they kind of take care of the linearity of the data, so that the network, the main network, which is these structures here, it kind of handles the nonlinear part of the data. So it's kind of distributing the data into two different parts. So just one intuition behind why do we have these kind of connections and all. And each of these structures have their own peculiarity. So yeah, that's there. Okay, so yeah, let's see. Now we'll discuss the a driving scene understanding problem. So I just want to go into details of this, just as a case study of how do we actually solve it and what do we do with it. So an autonomous car should be able to detect objects in an urban setting and highway setting, especially the urban, where there is a huge amount of objects and occlusions that are there. A convolutional network is pretty much a standard. And there are like special hardware that are designed around it. But then we also have the image data, that is more suited for object detections. But there is a problem there. The depth information is not there. And of course, if you go through some research papers and all, you'll see that mostly LiDAR is sort of used for depth information, or there is a stereo vision idea that where you have two cameras and all, and you use stereo vision. But so you kind of need some kind of a depth so that the three-dimensional position of an object can be sort of achieved. So let's first discuss a 2D object detection that is there. A camera-based 2D object detection, so it's a typical object detection tasks. You have a single stage detection where you have a YOLO, you have an SSD, you have a corner net, where all you have to do is you just have it in one stage detected. They're really fast, but they don't have that much of a good performance, and it makes sense because you can have bounding boxes all around the scene that you're having. So what do we do with it? Well, we have a double stage detector, which is like the typical one is RCNN or a faster version of it, where you have you have this candidate proposal and a bounding box classification. The problem is, as you can think, there is more processing involved, so it's a little slower. So what do I mean by that? Double stage detectors are hard to put in on a hardware. So again, all the decisions that we make from an autonomous driving point of view, the hardware plays a huge role, which is very sort of not trivial. And so that kind of creates a problem. Again, there are sort of hardware-friendly structures like MobileNet, SqueezeNet, that can run on embedded hardware. But again, we cannot just use any hardware. So that's another common question that I get. It's like, how about we just use a Raspberry Pi or these NVIDIA-based hardwares and all? Well, the answer is we can't use them because first of all, they're not industry grade. We have to take approvals from the highway authorities and all sorts of government organizations to sort of approve an hardware. So the hardware should be able to withstand the temperature of the surroundings, and it should be able to work in really, really cold, and of course in very hot. So I mean, you have to sell the car in all sorts of different climates. So these hardwares are good for having a proof of concept, but not for actual car that we have. So I'm here just showing a 2D object detection of an image, how it looks like, So how do we do it with the help of LiDAR? Let's see. With the LiDAR, we have this 3D object detection where the point cloud by itself, it doesn't have that much of a rich visual information. But when we combine with a camera with the LiDAR, you kind of use that mostly in production. So there are all sorts of different networks for that. I've pointed it out here. The voxel net, ROR net, multi-view 3D net. It's pretty common. One disadvantage, as I was mentioning, was that, simply put, LiDAR looks ugly. Nobody likes them on their car. And, customers won't put something on their car like that, even in spite of they getting a good autonomous driving performance. It's really hard to convince somebody. And then, of course, the cost. LiDARs are expensive. Just to give you an idea, a $10 radar sells around close to $200. So there's a huge margin there. So LiDARs are expensive, and the cost when it gets transferred to the customer, it's going to be expensive. So it's hard to convince a customer, hey, here is a sensor which is super costly, and it also looks ugly. So yeah, that's a problem. So one solution that we use is we use LiDAR and a camera data in our training, and then only use camera for the testing. So that kind of helps out. So there is a network called an avoid network. It kind of does that job, and it's very useful. So that's one way of sort of using LiDAR, but not sort of handling it onto the car. And you can do an offline training and get the network decent performance, and yeah, you can just deploy that onto the car on a hardware just using the camera sensor. So here I'm just showing one of the other urban setting problem where we have to do some kind of a semantic or an instance segmentation. Sorry. This is another way of understanding a scene in front of us in an urban setting. And what we do is we categorically label each pixel of the image. Now, why do we do that? Well, the main reason is it kind of helps us to sort of weed out every object that is in front of us, especially in a crowded place. Think of it like, I don't know, a Friday night of a downtown probably, or in any place like a shopping, grocery stores, that area where there's a lot of crowd. So it kind of makes sense if we can do any kind of pixel-based labeling on the scene, and then really figure out what is going on. So it also helps us in getting rid of the problem of occlusion, which is quite common. And then what do we do here? We mostly use encoder decoder based architectures, which is the unit based structures that we have. Segnet and AdaptNet is what we found to be very useful to be deployed on the production, which I mean onto a hardware. And again, it's not the segnet, the regular segnet. We have to do some tuning. We have to sort of shrink the size. We have to do mixed precision training, all sorts of things in there. So how do we specifically train a machine learning model for a hardware is another talk. And so yeah, that's another sort of a chapter. We also use a mask RCNN, which combines the detection and the semantic segmentation all together. So that's there, and I guess that's the last slide I have. And if there are any questions, let me know. Let's see. Yeah, there you go. Yep, that's all. Dr. Sansani, can you take over?
Okay, thank you very much, Dr. Kanish. I have one question from the audience. The first, the question is,
Yes,
okay, what is the minimum specification of LiDAR that used in automated driving system?
The minimum specification, again, depends on two things. One is the location of the LiDAR on the car. If it's, I'm talking Velodyne, let's say, just one of the LiDAR manufacturing. There are others also, so nothing special about Velodyne. But again, it depends on the location where the LiDAR is on the car. Is it on the sides? Is it on the front? And LiDAR. The second thing is what specific tasks are we thinking of, getting the LiDAR to work on? Is it creating a 3D point cloud in front of us? Let's say I'll take an example. Let's say it's in front of the car. So definitely I need a long range LiDAR, which kind of creates a 3D point cloud for, again, ideally I would like to have, let's say 200 to 250 meters. So that 250 meter is a good amount of distance in which if I have the scene in front of me and I can really tell the algorithms that, hey, there is this object in front of you within 250 meters. The algorithm has enough time to process and then sort of give the response. So it's kind of like a balance you have to have. If you have a smaller distance, let's say, I don't know, 100 meters. So the algorithm has to decide within those 100 meters what it looks like. So you need a really faster algorithm. But again, the sensor is going to be cheap because then it can only detect within 100 meters. So the larger the distance you can see, the expensive the sensor gets.
Okay. And next question is that if I need to use the offline hardware, microcontroller, microcomputer, or something else, for calculate all the data in one car, how many deploy offline hardware on the car that make the automated system always available?
I didn't got the last part of the question. Can you repeat it?
Okay, I think the question is how many deploy offline hardware on one car that make the automated system available?
Oh, I see. So how much of computation you require on the car to
Yeah.
make it work?
Yeah.
I can give us some an example setup. You pretty much need one single PC. I mean a system, preferably running Linux, having some data acquisition on it, and having a single GPU is enough. To do, when I say enough, means it's enough to do detection with a camera and a radar on that, and then able to sync it with the GPS and IMU and the wheel odometer. You're okay. You don't need that much. The main problem that comes in is, so you literally have to keep a PC in the backseat of your car. That's okay to do it, but you're not going to be able to sell it. So you can do a proof of concept for sure. Yeah, you can. But then when you have to sell it, you have to put it on a chip or something else. You know?
Right.
So that's a problem.
So what, I mean, how much is the delay time though? Then, I mean, the calculation time, the delay is.
Yeah. So we are talking to give you an example, a typical, let's say, stationary object detections in an urban setting. We would like to have it every machine learning stationary object detection to be finished for one frame within 100 milliseconds. So one decision has to be made within 100 milliseconds, because you have to remember it's just one sensor. You also have data coming from all the other sensors. So you cannot engage the hardware just with one sensor, because at the same time, it's also timing it. It's also seeing what the other sensors are doing. So you want to reduce the time. But just to give an idea, again, it's just a ballpark number. 100 milliseconds it takes for one decision to be made. Let's say, to tell a machine learning algorithm to say, hey, there is an object in front of us within 100 meters with 90% confidence. So.
Wow. Yeah. And next question is that, can we estimate the cost of our hardware in one system? Roughly.
So again, yes, you can. I mean, but then when I said custom-made hardware, I frankly don't know the price for that. I mean, I'm sure. But then just to give an idea for somebody to get it started, let's say you want to put, I would say take any typical PC. Again, no, I'm sorry, I'm saying PC. I don't mean Windows. Put a Linux. I mean, that's mostly what we use. Put a Linux. I would say any system that any desktop-based computer is going to work. So whatever is the cost for that is the cost for this. And then you know, in terms of putting the camera, we have all sorts of cameras in the market. I mean, Mobileye has a good one that does all sorts of. It has a good API actually to do the detection, so that's pretty good. But then, in terms of having a grad level school project kind of thing, I would say forget the car. Actually, just do it on a robot. On a small, like a 4-legged robot, that's enough. That you can put a camera. I mean, a Raspberry Pi level camera is good enough. And I've personally worked on it, so I know it works. That you can just put a Jetson Nano or a Raspberry Pi or any of these boards. I mean, I don't have experience with Arduino, but I know Raspberry and Jetson should work. And I would say, yeah, if you want a cheaper, low cost, you probably should start with a robot.
Yeah. Okay, and next question is, it seems like object detection and semantic segmentation are done in frame-by-frame basis. How can we make use of temporal information by making prediction on consecutive frames?
Oh,
that's the first question.
I see. That's a good question. So yeah, that's actually a very practical thing. So what we do there is one thing that I skipped. I didn't realize somebody's going to ask such a detail. One thing that we do is we don't really do prediction every frame, because if you think about it, a car in front of you, it's gonna be pretty much the same. Let's say in the third frame also, it's so you're kind of wasting the resources. So what you do is you do the LSTM. LSTM takes care of the sequence every frame, and then the convolution net. Let's say the convolution net takes care of the detection every fourth frame. So there is a timing in both of them.
Okay.
LSTM tells you, hey, you're still on the same car that you saw fourth frame behind you. And convolutional net says, okay, assuming that the LSTM is correct, here is what I think. It's still a car. It's still in front of us. So you kind of have to have a timing. So what we really do is we actually have a kind of like a global timer, which times all these things on multiple threads. So each of these sensors are running on each single thread. If I talk in terms of, like a software point of view. So each of these sensors and each of, not just the sensor, each of these algorithms, we make sure it runs on just single thread. But that creates another problem. Single thread running, you need to be really fast.
Yeah.
You can just sort of, so that kind of avoids us to use those heavy deep learning models. We just can't use off the shelf. That's what I was saying. We can't use off the shelf deep learning models.
Yeah. Okay. And next question is the same person asking, what can we use to perform object tracking from the outputs of CNN?
What can we use?
Yeah.
Oh,
The tool maybe. Yeah.
You mean there are tons of papers on that. I mean, I would say the way if you want to ask, like the way we do it in our R&D is mostly the Kalman tracking is the gold standard. So any tracker you bring, you have to compare it with that and see how good it performs. But in terms of doing an object tracking with machine learning, oh boy, there are like tons of papers on that. I mean, tons of GitHub code. So yeah, just pick any, frankly. The problem that you're going to face is not the model. Actually, the problem you're going to face is the corner cases that you see. Again, it's autonomous driving is like medical or healthcare. It's a critical systems. You cannot just say, oh, my model works 95% correct and 5% it's wrong, because 5% wrong might lead to a death.
Right.
So you have to be very careful, and that kind of that's actually another question that I mostly get. Autonomous driving is intentionally slow. There is a reason for that, and the reason is this: it leads to human. I mean, it's connected to human lives.
Right.
So you can't put you can't just put up say, oh, the accuracy is 99%. What about the 1%?
No, you can't.
You can't do that.
You are not allowed to have a mistake.
Exactly. So the KPI or the key performance index are very different than compared to, let's say, in all these papers and all that we see.
Yeah. So how slow is the car moving then?
Oh, the car, there is no speed limit on that.
So how slow that you recommend? I mean, how fast that you recommend for it to work?
So while we are testing it, again, these are specifications of the National Highway Authority, NHA, in North America. We have to test the car at around 130 miles also. 130 and 150 miles. Also, we have to check it.
Wow, really? So your ultimate car is moving like 130 miles per hour?
Yeah, when I say that, I'm not saying that the people are driving that fast. I'm saying when you have an algorithm, it should be able to perform even at that speed. That's when you get it approved. So there is a lot of government agencies involved in this. So getting something onto the product level or to the customer, it takes time. But all the if you want to ask me from a research point of view, you drive. The slower you drive, the better it is for me, because the algorithm gets more time. I mean, it's good for me. But then let's say you're driving in an urban setting. Most of the time, the drivers in an urban setting have 60 to 70 miles is mostly max. But then you don't really say that, okay, at 80 miles my algorithm is going to have a lower confidence. No, you have to have around 130 miles is mostly the limit, where you say, okay, still at 130 miles it's going to work.
Okay. Okay. And I don't see any questions, so I think we are done now. So
Okay.
thank you very much, Dr. Kanish, for coming to give a nice webinar and a pretty, wow factor for me, I guess.
Well,
So
thank you so much.
Thank you so much.
Yeah, I appreciate it. Thank you for the opportunity. Really, I appreciate it. Thank you.
Okay, thank you all the audience also for coming, and good night, everyone. So I'll see you next time.
Yeah. Okay.
So
All right. Thanks.
Okay, thanks.
Thank you.